Section 6.6 is called generating permutations and combinations. That means how do we create the different arrangements or combinations that would be in a situation. Think about what's generally called the traveling salesman problem. This means that if you have a number of cities that a salesman has to visit, and the travel times to travel between the cities, what would be the best pathway to minimize the travel time to get from, the beginning point to all those cities and then back to the beginning point? Or finding a subset of a set with a particular characteristics, like how many subsets are there of a set with 10 elements, where the subset has only 3 elements, or finding a team of employees that together have a certain list of skills, and so you're bringing together a task force or a team with a certain number of skills that you're picking and choosing what skills should be on that team. These are all possible applications of the ability to generate permutations or combinations of sets. Okay, so many of these tasks can be done by hand, and most of these problems in this section will show the by hand method, but we can also use algorithms. These types of calculations or generating permutations and combinations can be shown using algorithms. Okay, now first we need to discuss what lexicographic ordering means. Lexico has to do with kind of like a dictionary, dictionary order, or lexicographic ordering of a set of permutations of the numbers 1, 2, 3, 4, all the way to n. So we have some set of numbers from 1 to n, and we're going to order that set and think about the ordering of that set. Now, A1, A2, A3, dot, 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 all the way to AN will precede or come before B1, B2, B3, all the way to Bn, if for some k value, with k being between 1 and n, and then you have A1 equal to B1, A2 equal to B2, A3 equal to B3, so all of the first few elements in the permutations are the same. All of those are the same up until k minus 1. But then there's some point where the kth element of the first thing is less than the kth element of the second thing. So in other words, a permutation of a set of the n smallest positive integers, and that's this set we're talking about at the beginning, 1, 2, 3, all the way to n. That permutation will precede, in lexicographic order, a second permutation if the number in this permutation in the first position, where the two permutations disagree, is smaller than the number in that position in the second permutation. Okay? Basically, this is the same as what we do when we alphabetize 2 words. Okay, if we have 2 words and we want to alphabetize them, we look at the letters at the beginning, and if they're the same, then we try to find when they start to change to be different. Okay, so here's an example. The number 341067 is in lexicographic ordering before, or it precedes, 341069. Now notice the first several digits, the first 5 digits, 34106, they are the same in both numbers. And then you compare the next digit, the 7 with the 9. Now because the 7 is less than the 9, then in lexicographic order, the first one will precede the second one. All right? So like I said, this is because the first 5 digits are equal, but looking at the 6th digit, the 7 and the 9, 7 is less than 9, so the number 341068 is going to be less than 341069. All right. Now, if I ask the question, which permutation of the same digits immediately follows the permutation 3, 2, 4, 5, 1? All right. Now, we got to use those same digits, 1, 2, 3, 4, 5, basically. But we want to find the permutation that immediately follows, the very next one that follows 3, 2, 4, 5, 1. Okay. Now, here's the key how to do this. First, try swapping the last two digits. Now, 3, 2, 4, 5, 1. If I swap those last two digits, it'd be 3, 2, 4, 1, 5. Now, would that be greater than 3, 2, 4, 5, 1? No, it wouldn't. And so the next sentence I say, since a larger permutation is not obtained by interchanging the last two digits, consider permuting or rearranging the last three digits, or in other words, rearranging the third, the fourth, and the fifth digits, so that instead of 4 for the third digit, we use the next highest number. Okay, so instead of 4, let's put the 5 next. Okay, so this yields either 3, 2, 5, 4, 1 or 3, 2, 5, 1, 4. So if you put the 5 in the third position, because it's the next higher one after the 4, then you have left over the 1 and the 4 to place. And if you put the 4 next, that's not the next one. The next one would be the 3, 2, 5, 1, 4. But 3, 2, 5, 1, 4 is lower, so that would follow the 3, 2, 4, 5, 1. So we're trying to find the next permutation that immediately follows 3, 2, 4, 5, 1. And it'll be 3, 2, 5, 1, 4. Okay, there's some other examples on page 435. Let's take a look at this. So example 1 on page 435. This is very similar to the one I just talked about. The permutation 2, 3, 4, 1, 5 precedes the permutation 2, 3, 5, 1, 4, and you can look at why that's the case, because the 4, 1, 5, if I replace the 4 with 5 and then I use a 1, 4, then that would be the very next one. Now, example 2 says, what is the next permutation in lexicographic order if it's 3, 6, 2, 5, 4, 1? Okay, now would it work to just swap the last two digits? Would that give us the next permutation? Well, no, it wouldn't, because it would actually give you a lower permutation. So you can't do that. Then look at the next digit over, which is the 5. Okay, now 5, we'd have to replace the 5 with a 6, so that wouldn't, I can't use a 6. I've already used it in the earlier digits, and so I can't like interchange the last 3 digits and try to get a value that's any higher than that. So then I look at the last 4 digits. So how can I rearrange the last 4 digits? Okay, well, like I said, I can't change the last 3 or the last 2, but if I change that 2 to the next higher number, which is a 4 from the ones I'm working with the last 4 digits here, and so I can change the 2 to a 4 and then rearrange the other digits to be the smallest possible after that. And so that's why you get this number that I've got highlighted right there, 3, 6, 4, and then 1, 2, 5. 1, 2, 5 is the lowest permutation for the remaining digits of 1, 2, and a 5. Okay, so study that, think about that. That's the next highest permutation after that given permutation. All right, algorithm 1 gives a way for a computer to generate the next permutation of a set in lexicographic order. So now let's look at generating permutations. So how do you generate all the possible permutations for a particular set? Now with a small set, it's not difficult to generate all the permutations of a set. Now if you just have one object in the set, then of course there's only one arrangement of that. If you have two objects in the set, there's two arrangements, because you could have the first one first and then the second one, or vice versa. If you have three, it's not just three arrangements. Let's look at this example. Generate the permutations of the integers 4, 5, and 7. Now, we're going to try to start with the lower numbers and put them in the leftmost positions, and then do all the possible arrangements of the remaining letters. So we start with the lowest number, which is 4, and then we put the next lowest, which is 5, and then the next lowest, which is 7. But then to get the next permutation in lexicographical order, we would switch the 5 and the 7. So 4, 7, 5. Now the next higher number than 4, we would use 5 next, not 7. We would go with 5 next, because we're trying to keep the lowest possible numbers. And then 4, 7. But then we could switch those digits and get 5, 7, 4. And then last of all, we do the highest number, 7 first, and then 4, 5, and then 7, 5, 4. So this is in lexicographic order, and it gives all the permutations. Now, the formula for finding how many permutations you'd have if you have 3 objects is 3 factorial, because there's 3 options for the first position, then 2 options for the second position, and only 1 option for the third position once you've chosen the first 2. So 3 times 2 times 1 is 6, and that's how many we had here. There's 6 permutations for those numbers 4, 5, and 7, or for any 3 things, okay? Now what about generating the permutations of the letters in the word boat? So we have now 4 things in the set. We got the letters B, O, A, and T, and so the permutations is 4 permutations, or from 4 choose 4. So we're choosing 4 letters from 4 letters and doing permutations. The formula is n factorial, so that'd be 4 factorial, over n minus r, but n and r are both 4, so you get 0 factorial. Now 0 factorial is not 0. 0 factorial is actually 1. Okay, factorials always are 1 or higher. They're never going to be 0 or anything negative or anything like that. So that's 4 factorial over 0, or excuse me, over 1. And so 4 factorial is 4 times 3 times 2 times 1, and that gives you 24. So there are 24 possible permutations of those 4 letters. All right, and here they are. A, B, O, T, A, B, T, O. Now notice we're starting with the lower ones first, but and then we have to swap letters and get the higher ones. So I've done all the ones with A and B being our first 2 letters, A, B, O, T, A, B, T, O. Then you go to A, O, B, T, A, O, T, B, and then A, T, B, O, and A, T, O, B. Now that's all the ones starting with the letter A, and I've color-coded these. Now let's go on to start with the letter B, the next higher number or letter. So B-A-O-T, B-A-T-O, B-O-A-T, B-O-T-A. and then BTAO, BTOA. All right, then we'll go to the next letter, O. So OABT, OATB, OBAT, OBTA, OTAB, and OTBA. Those 6 there too. And then TABO, TAOB, TBAO, TBOA, TOAB, and TOBA. Now notice that last one is in total reverse order from the first one. ABOT, the total reverse order is TOAB, or BA, excuse me. Anyway, you can see that there is 6 times 4, or 24 different arrangements of that letter, of that word, boat. Now, those were permutations. Now we're going to talk about combinations. Combinations could be thought of essentially as subsets of a set, okay? Because you don't care about the order, and neither when you're forming a subset, you don't care about the order. You just care about what elements are in that, okay? Now, each element of the original set, you have 2 choices. You could either accept that element into the subset, or say no to it and not accept it. So this actually corresponds to a binary situation, the number of bit strings of length n. Okay, so combinations or subsets of a set with n elements can be placed in a one-to-one correspondence with the number of bit strings of length n. Because a bit string, you can only have a 1 or a 0. There's always, 2 options in there, just like with subsets. And let's look at why that's the case. Suppose there are 5 faculty members in a department, and sometimes they show up to football games. Now, it could be that none of them come to the football game. It could be that 2 or 3 of them, or maybe all 5 of them come to the football game. So the question is, in how many combinations can these faculty members show up or not show up for the game? Okay. So for each of these faculty members, there are 2 situations. They either show up or they don't show up. Thus, there are 2 to the 5th power, or 32 combinations of these coming or not. And the bit string 00000 corresponds to none of the faculty members showing up, while the bit string 10010 might correspond to the first faculty member showing up, because you have a 1 in that position, in the first position, and the fourth faculty member showing up. So you can see how there's a parallelism between the set of people that are possible subsets of the set of those 5 faculty members, and bit strings of length 5. Okay. Now, let's talk about generating the next larger bit string. Okay, so it says find the next largest bit string for the bit string 110110111. Okay, now the next largest bit string, you would have to basically increase one of the digits by 1 unit. And if you increase one of the 1s by 1 unit, it kicks it up to the next higher unit. But so the easiest way to do this is simply to take the rightmost 0. In other words, the 0 that's on the farthest to the right position. So you see that this 0 right here is the rightmost 0. If you just change that to a 1 and then replace all the digits to the right of that with zeros, that will give you the next bit string in lexicographic order that's just immediately higher than that bit string. So we're going to take this 0 on the rightmost side and change it to a 1, and then change all these 1s to the right of it to 0s. And so that's why I ended up with 1 1 0 1 1 1 0 0 0. All right, so you change that 0 here to a 1, and then change all the 1s after that to 0s. It's almost like you're going 9 and then increasing it to 10. 1 0, you know, in our decimal system. But in the binary, you know, change them all to zeros after that. Or it's like, you know, if you had 999, to go the next one up, you make it a 1 and then make it 0 from then on after that. So you get 1,000, right? All right, so example 4 on page 437 gives another example of showing how to generate the next bit string and hence the next combination in that order. And it uses the same idea. It's changing the rightmost 0 digit to a 1, and then all the digits to the right of it get changed to a 0. Get changed to a 0. Okay? But you can look at that on page 437. All right, then if you were given a problem that said find the next 4 combination, that means the next subset with 4 elements in it, basically. Okay, 4 combination. In other words, combination of 4 of those items. When the set you're choosing from is 2, 5, 7, 8, 11, and 15, but you're trying to find the next 4 combination after the combination 2, 7, 11, 15. 2, 7, 11, 15. All right? Now, one way to consider this, the easiest way to do this, is to create a bit string from that subset that you have. In this case, 2, 7, 11, and 15. Now, 2 is in the first position of the set. 7 is in the third position. 11 is in the 5th position. And 15 is in the 6th position. All right? So that corresponds to the bit string 1, 0, 1, 0, 1, 1. Because you have a 1 in the first position, a 1 in the third position, a 1 in the 5th position, and a 1 in the 6th position. But the other ones are zeros because you don't have those included in the subset. So it's 1, 0, 1, 0, 1, 1. Now, the next bit string higher than 10, 10, 11 can be found by changing the rightmost 0 digit, just like we did up here. The rightmost 0 digit got replaced with a 1, and then everything after that became a 0. So similar to what you're doing here, you're going to change this 0 here, which is in the 4th position, to a 1. But you have to have 4 elements in your set. So you can't say change that to a 1 and then make everything else a 0. You just change that to a 1 and then you put another 1 in. It has to have 4 1s. Okay, it has to have 4 1s. So 2, 7, 8. You change the 11 basically to an 8, and then the 15. Okay, so 2, 7, 8, 15 is the next 4 combination for that set. All right, so algorithms are in this section that help you generate combinations. And we're actually not going to hold you responsible for knowing these algorithms and how to use them for the quiz or the exam. But I just want you to know that they're in that section, and you can use these algorithms for generating either the next larger bit string in algorithm 2, or in algorithm 3 it generates the next R combination in lexicographic order. Kind of like what we just did with that previous example with the sets. And so you can look at these if you want, but like I said, you won't be held responsible for it. Now, there's one more item that we want to look at because it's in the homework. This item is Pascal's Triangle. Now, I don't know if you have seen Pascal's Triangle before. Pascal's Triangle comes into play in many different math situations. Many different math topics relate to Pascal's Triangle. First of all, you start Pascal's Triangle putting a 1, and then you always add 1s along the left diagonal and 1s along the right diagonal. And then, as it says in yellow here, just add the 2 numbers above to get the next row. So, like for example, the 1 and the 1 added up to give me a 2 in the middle here. And then the 2 and the 1 add up to the 3, and the same thing here. 1 and 2 makes 3 here. And then 1 and 3 makes 4. 3 and 3 makes 6 in the middle. And then 3 and 1 make 4. And if you keep coming down like that, you always add the 2 above, either above and to the left or above and to the right of that particular number to get the next number. So what would be the next row? Well, you'd start with a 1, and then the second item in that row would be 1 plus 6 or 7. The next item would be 21, 7 plus 15. The next item then would be 35, and then another 35, and then another 21, and then 7, and then 1. And as you've noticed, Pascal's Triangle is symmetrical. All right, so what is the significance of Pascal's Triangle to what we've been talking about? Well, for any item in a row, where the row number starts at 0 for the top row, and then 1 for the next row, 2, 3, 4, etc. Any item in the row and in position K starting from 0, so this would be like the 0 position, 1 position, 2 position, 3 position. The item is equal to the combinations of n things taken r at a time. So Pascal's Triangle relates to combinations, and the formula we had for combinations. Okay, so it's combinations of n things taken r at a time. So let's look at it for an example. The item number 6-2, which means row 6, item 2. So row 6 is this row right here that has a 6 as the second position. Actually, that's in the first position. The first position in any row is position 0. So position 0 is the 1. Position 1 is the 6. Position 2 is the 15. So 15 is row 6, position 2. All right? So that 15 has some significance when we talk about combinations. And the significance is that there are 15 ways to choose 2 objects out of 6. So you've got a set of 6 objects. There's 15 different ways we can choose 2 objects out of those 6 objects and form a subset. So it's basically there are 15 2-element subsets or combinations when we choose 2 things out of 6. So that's an interesting fact that we can actually use Pascal's Triangle to do some of these calculations. If you wanted to carry it down higher and higher rows, we could basically do all the math problems involving combinations from Pascal's Triangle. So I hope you have found this interesting, and I wish you well on the homework. It's up to you whether you practice and do these problems and succeed. I mean, I'm here to help if you ask questions, but you have to ask. All right, have a good night.